Welcome to Chapter 8. We will talk about elimination reactions and alkenes. Alkenes are the products of the elimination reactions. This is a substitution reaction, and it is a review from the previous chapter. And if you remember, in a substitution reaction, we're substituting the nucleophile, which is this nucleophile, it's a Lewis structure, for this electrophile. And we do a backside attack because this is a secondary alkyl halide. And that would be inversion of stereochemistry. And so that's an SN2. Which of the following is the correct product for the reaction below? Tosylate is an excellent leaving group, just so you know what tosylate looks like. That's toluene. Toluene sulfonyl oxygen, and that's an excellent leaving group. Now, this is a weak nucleophile. Notice that it doesn't have a negative charge, and so that's methanol. That would be a polar protic solvent. When the solvent is the nucleophile, that's called savolysis, so if you did your reading. And so this is a secondary alkyl halide. So it can go SN1 or SN2. So in this case, because of these conditions, and this is a good leaving group, you're going to get an SN1, which means we've got to get a carbocation intermediate. Now you want to classify that carbocation, and it can do a shift to more stable carbocation. So a tertiary carbocation intermediate is going to be more stable than a secondary or primary. Primaries are pretty much not stable. Also, benzyl carbocation and allylic carbocations are going to be up here, more stable for like a tertiary carbocation in an SN1 reaction. So this is a secondary, because you look at the carbon, this is the carbocation, and you say, how many carbons is this carbocation bonded to, this carbon? It's 2, so it's a secondary. So that means we got to look at 2 neighbors. If we trade places with this next door neighbor, it would become a primary. That's not more stable. Primaries are less stable than secondaries. If it traded places with this neighbor, it'd be a tertiary, and that is more stable than a secondary. So what happens is this has a hydrogen, and it will do a thing called a hydride shift. And that means this hydrogen takes its 2 electrons to make a more stable carbocation. So what happens is it just trades places. So that hydrogen goes here on that carbon, and then this becomes the carbocation, and now your nucleophile comes in. Your weak nucleophile will come in to this carbon here, and you get OCH3. You do still have this proton there, and then another methanol. We'll just do a deprotonation. And now, because the carbocation is an sp2, it's flat. Because remember, that's planar. So that means the nucleophile can come from the top and the bottom. And when it comes from the top and the bottom, you get a racemic mixture. So you can just do that by not showing stereochemistry. So C is your answer, and it would be C only. So how do you predict between SN1 and SN2? Well, the key is here is your nucleophiles. So if you have a secondary substrate, your electrophile, your substrate. If it's secondary, then it can go either SN1 or SN2. And so then you have to look, is your nucleophile weak? If you have a strong nucleophile and polarity protic, it's going to favor SN2. So you can see that if it's primaries, these all go fast. Primaries, methyl, alkyl halides, we're talking about the substrate, benzyl, allylic, these are all going to be SN2. However, when you get a tertiary, tertiaries undergo SN1, they will not go SN2. So that's here. Strong nucleophiles will favor SN2. Protic solvents, that's like methanol and water. Weak nucleophiles, that means no negative charge, will favor an SN1. All right, so now for chapter 8. Okay, so you have now, instead of a nucleophile, you have a base. And what makes the nucleophile a base is it actually goes after a proton. And so the proton has to be, so this is your alpha carbon is bonded to your leaving group. And so then you want to locate your beta. You can look at all your betas and you look for a beta hydrogen. And so the base is going to take the beta hydrogen. You're going to get, on this one, you're going to get 3 curved arrows in your reaction mechanism because those electrons are going to do like a backside attack. This is actually an E2 mechanism, and it's going to be concerted. I mean, this is all happening at the same time, so we're going to show all 3 arrows, and that's how you get a new pi bond. And you see that the base picked up the hydrogen, so there's that. And these are the electrons for this bond. And then these electrons here became this new pi bond. And then the electrons on the leaving group went with the leaving group. And so this is going to make an alkene. You'll learn in chapter 11 that these are going to be your starting materials, and we'll do a new mechanism. So this is your functional group. On this chapter, eliminations always make alkenes. And that's your functional group. So we're going to start with alkyl halides, the same starting materials. And now we're going to have, instead of a nucleophile, it's going to be the base. Now this is going to be challenging because nucleophiles are bases, right? Except they go after the carbon. So you're going to have to understand the conditions in which you're going to get an alkene versus a substitution reaction. And you're going to deal with either an E2 or an E1 mechanism. So if you add this to your other mechanisms, you got SN1, SN2, and now you're going to have E1 and E2. And E1 and E2 always make an alkene. SN1 and SN2, you substitute the nucleophile. So the nucleophile is substituted for the X, the leaving group. So all of them have the same substrate with a leaving group, but if you do a substitution, the nucleophile becomes part of the carbon compound, and if you have an elimination, you're always going to make an alkene. So this is elimination of HX. So once again, you still want to do your substrate here, and you'll see that this is a primary alkyl halide. But what you'll learn here is this is potassium terbutoxide. This is a bulky base. Okay, so this is non-nucleophilic. Okay, so this is going to act as a base only because it's so sterically hindered. See the sterics? Now you got to understand that these carbons are like those big propellers, folks. I mean, they're rotating around just like those electrical propellers out west, where they are huge to generate wind energy. So they're sterics. And so this is going to go and take, this is your alpha always, and I want to see this in your POGIL. Label the alpha carbon and the beta hydrogen. So I want to see that in your mechanism. So here we identify if it's a primary, there's only one carbon neighbor. So you only have one hydrogen to look for. This big bulky base, not a nucleophile, will take that hydrogen, and then this will push those electrons here to make your alkene, and then these electrons will leave. And so count your carbons. You have 1, 2, 3, 4. 1, 2, 3, 4. This makes 1 butene. And newer ways put the 1 in the middle of the name. This is old school. This is new school. Okay, here we have a secondary alkyl halide. That carbon, the alpha carbon, is bonded to 2 carbons. And so your beta hydrogen here is now secondary. You have a strong base. And so here we go. And there's this, the alkene. And that's elimination. Sometimes if I might say choose the major elimination product. So look for that in a question, and then you know that you're going to choose an E1 or an E2 mechanism. If I say choose the major substitution product, then you would do an SN1 or SN2, and then that's how you would know. So read your question twice, on these quizzes and exams. If I don't say that, then I do expect you to be able to figure out between elimination or a substitution. So this is called dehydrohalogenation. D in organic chemistry means kind of to take away. So dehydro, that's a hydrogen, and a halogen, right? So that's dehydrohalogenation. You're taking the beta hydrogen, and this is your leaving group. And so you notice here that you've got your alpha carbon labeled, and you got your beta, and it's showing you that the base is going to take the beta hydrogen. And this is your mechanism. Now, so I think of that Mega Trainer song, all about that bass, no trouble. Okay, so you're going to look at these different bases, and you're going to have to really get good with the bases. The bases all have a negative charge if they're strong, just like a strong nucleophile. Sodium hydroxide and potassium hydroxide, these are going to be your inorganic bases because they don't have any carbon. That means they're going to be soluble in water. Usually you're going to have water. These are all strong. Sodium methoxide, these can be put like in methanol or ethanol, which is more of an organic solvent. But these are still polar protic solvents, just like water. And then you got potassium terbutoxide. This is the only one that's non-nucleophilic, and it will be because it's sterically hindered. These are called your alkoxides because they have O carbon. Okay, so here, just label your alpha and beta. Here you see you have an alpha carbon, and now classify it. It is a tertiary, so that means you've got to label 3 betas. Now the question is, which beta hydrogen will the base choose? Okay, and so here, sodium hydroxide, and it chose this beta hydrogen. And I'm going to tell you why soon, to give one alkene. Now, the reason why is because this is the most substituted alkene. So you count how many, so you find your alkene, this is your alkene, you say 1, 2, this is di-substituted because there's 2 carbon groups coming off of the alkene functional group. The more substituted alkene is going to be the more stable. And so more stable would like to be formed. Here you have, it's very sterically hindered, and so you can get 2 of these here. This is a secondary, and so we have 2 beta hydrogens, and this is going to be a mono-substituted, and this is going to be a di-substituted because you have 2 carbon groups. Alkenes. This one's going to be more thermodynamically stable than this one, and you'll see that this sterically hindered lots of times gives you the least substituted. Excuse me, alkene. And we're going to call that, you'll see that that's called the Hoffman product. The more substituted is called the Zaitsev product. So let's talk about the alkene. It's sp2 carbon. So sp2, sp2. So that means that its shape is planar. So it's flat like a piece of paper. And these groups are 120 degrees from one another. So you do not have rotation. You have a top and a bottom, and you have unhybridized p orbitals. So these are unhybridized p orbitals here, because what's forming these covalent bonds is this sp2 carbon hydrogen bond. Hydrogen just has its 1s overlap, and then this has its sp2 hybridized, so it's got 33% s and it's got 66% p shape in that orbital. And since sp2, you know you have an s, and then you have a px and a py and a pz in your atomic orbitals. And if you take 2 p's and 1 s and you do this to make this shape here for these, then you're left with a p orbital, and we call this an unhybridized p orbital. And so that is what constitutes a pi bond. You have to have this overlap, and those electrons can be there in the pi bond. Okay, so we classify alkenes by how many R groups there are bonded to the alkene. See, the most you can have is 4. This is a tetrasubstituted, and this is going to be the most, we call that thermodynamically stable. Okay, so this is the most thermodynamically stable. If you only have 1 R group, this is going to be the least. And studies have showed that. So one of the things you need to be able to do is rank the following compounds in order of thermodynamically stable from the most to the least. So when you look at this, hopefully you can see that this is mono, this is di, this is tri, and this is di. Now notice we have 2 dies, okay? So you have the alkene here, and you have, so what you want to do is you want to cover up and just look at 1 carbon and say what 2 groups. This is a carbon and this is a hydrogen, and you're going to learn to determine whether this is cis or trans. And it's kind of like you have to assign priorities, just like you did in chapter 5 for stereochemistry. So here you're just comparing the two because there's just two here. Carbon is atomic number 6, hydrogen is atomic number 1. We agree that 6 is greater than 1, so this gets the number 1 priority. And then we look at this other carbon of the carbon-carbon alkene, and we say, okay, we have a carbon, and we draw on our hydrogen. Well, you got a 6 and a 1, so 6, and see if you have 6 on opposite sides, because those are the higher priorities, that's going to be trans. Okay, you come here, and you can draw on your hydrogen, so you got a carbon and a hydrogen. That's a 6, and that's a 1, so this is your higher priority of those two. Here you draw on your hydrogen, and you go, okay, a 1 and a 6. Well, 6 is the highest. Oh, they're both on the same side, so that's a cis. And so if you're comparing both di-substituted, the trans is going to be more stable thermodynamically than the cis. So now you can rank them. C is going to be the most because it's tri. And then between these two, you're going to have the trans, so that's B. And then you're going to have the cis, which is D, and then the mono is the least. So CBDA. CBDA is the answer. Okay, so you do have cis and trans isomers. These are stereoisomers. So remember the isomers, they have the same molecular formula, but they have the same connectivity. If they had different connectivity, they would be constitutional isomers, but they have the same molecular formula, same connectivity, but they have a different orientation in space. And now you know in stereoisomers you can have enantiomers and enantiomers, or you can have diastereomers. And cis and trans are diastereomers. And the reason why is because you don't have free rotation. So whenever you don't have free rotation, you're going to have cis and trans diastereomers. We saw this in the cyclohexanes, and that's what this is showing you. So we can't rotate this. So here this is cis. The R groups are on the same side. Trans, they're on the opposite sides. They do not, these are different compounds. They are diastereomers, and if you remember, diastereomers have different melting points. They have different melting points, different boiling points. They can have different solubilities, okay? So they have different physical properties. So you're looking at these groups on each side, and you need to assign priorities to determine. And you have to decide whether you have cis and trans. Also, you're going to learn, you need to memorize cis is designated with Z in the name. Trans is E. I think of E.T., the movie E.T. Phone Home. That was my first movie in the movie theaters once upon a time. Okay, which of the following show cis and trans isomerism? So some of these don't. So you'll see that, do you see that this has a hydrogen and a hydrogen? If you have same groups, then you have no cis trans. So how would you name that? 1, 2, 3. It would just be pro 1-ene. Okay, this one you do because carbon and hydrogen are different. And then with the carbon, this would be number 1. And then you would look at the other one and say, okay, carbon and hydrogen are different. So what two things on each carbon of the alkene bond? And so since those are on the opposite, you would name this is a trans, which is also E. So it would be 2E, and it would be 1, 2, it would be but 2-ene. And that's how you would name this. This compound is no, because this carbon has a CH3 and a CH3. These are the same thing. So no cis trans isomer. D does, because hydrogen and carbon are different. And then on this, we have hydrogen and carbon are different. And the 1 and 1 are the same size. So this is cis. So this would be to Z, and then that would be but-2-ene. So B and D have cis-trans isomerism, B and D only. So this is talking about the stability of trans alkenes. So you're going to find that they're more stable than the cis. And that's because the double bonds are further apart, reduces the steric interaction here. They're less stable, more stable. And so here's a stability pattern here indicating that if you have a tetrasubstituted alkene, it's going to be more stable. And then also if you have an internal alkene, it's going to be more stable than an external. Um, this is just talking about, um, so when you have sp3 carbons next to each other, like CH3, each one of these, actually, this sp3 carbon, um, can donate electron density. And that's another reason why these can be more stable. So most things are explained by sterics and electronic factors for when you're dealing with stabilities and why molecules or functional groups behave the way they do behave. Okay, so when you're looking at butenes here, this is a trans butene. A lot of times you'll see trans, or you might see it as 2E. This is a cis. You might see that as 2Z in the nomenclature. And then this is mono. So you see that the trans is more of a disubstituted alkene is more stable than the cis, and the cis disubstituted is more stable than a monosubstituted. Now this is how to synthesize alkenes. We're going to do elimination in E2. The 2 stands for bimolecular. E1 stands for unimolecular. So the E2 mechanism is the same rate law as an SN2. Okay, so you got your substrate, and then the concentration of, in this case though, it's going to be a base instead of a nucleophile. And the kinetics are second order. It's also concerted, so it's all happening at the same time. And this is where I'm showing you, you want to label your alpha, which is where your leaving group is, and then your beta carbon. This is a tertiary, so it's got 3 betas. So you can label all your betas. You got 3 betas because it's tertiary, but the beta hydrogen that's going to get deprotonated is the one that's more substituted. So the more substituted beta hydrogen is the one that's going to be removed. And in doing so, that's going to give you the more substituted alkene product. Now that isn't always, and I'm going to show you when that doesn't always happen and what conditions, and you will be expected to know that when we come to that. And that's showing you the mechanism. So this is the mechanism that you're expected to be able to draw, and you're labeling your alpha and beta, and this is the beta hydrogen that is going to get deprotonated to give you the disubstituted alkene product. And when it's the more substituted alkene product, we say that this is a Zaitsev. You might see it written this way, and or sometimes it's Zaitsev. Some people write it with an S, some people write it with a Z. I think I do Z. Okay, so the reaction energy diagram is going to be very similar to the reaction energy diagram of an SN2. You just have this one peak here. The only thing that would be different would be this transition state. and you would see that the base is forming this dotted line to the beta hydrogen here. So the bonds being broken and made at the same time are in dotted, and this is your leaving group. So the transition state would be different. Okay, so what bases? You need to really get familiar with the type of bases. I would write them down on a piece of paper and kind of get familiar with them. They're strong. E2, you're going to see they're going to have a negative charge. So your alkoxide, your hydroxide. But sometimes you want some sterically hindered bases. Um, and these are examples DBN and DBU. And so here's an example of DBN, and this is your alpha, and this is your beta. And so that hydrogen gets taken, and there you get your new bond. This is a secondary, but it only has one beta hydrogen. And this shows you a prostaglandin synthesis in which an E2 reaction with the strong base was used. Okay, so the leaving groups, the better the leaving group, this is no different than your substitution. The better the leaving group, it's also going to be better if you use polar aprotic solvents. It's going to be faster reaction. Um, now this is different, okay? A tertiary alkyl halide um, will be your fastest E2 in an E2 reaction, fastest substrate in an E2. Now, if you remember, a tertiary will not undergo an SN2. And the reason why, if you have a base here, you're going to look at this is your alpha. One of these is your beta hydrogens. So if you have a base, it's taking this. So it's not a sterically hindered issue anymore because the base can get to the beta hydrogen in an E2. Remember, in a tertiary, substrate won't undergo SN2 because your nucleophile can't get into this carbon that's sterically hindered. So the rate of an E2 reaction, your tertiaries are going to be your fastest. So to increase the rate, they're just talking to you. We're going to go into the transition states of E2 mechanisms and why you would when you would get Zatsev's product. And Zatsev's product is going to be the more substituted. And how you do that is you label all your beta hydrogens, and then you're going to go and abstract the beta hydrogen that has the most carbons. And that's always going to give you your more substituted thermodynamic. So here, take the time to do the alpha and then the beta. So this is a primary. See, primary, so it only has one beta. So you don't even have to worry about it. There's only one beta hydrogen, and that's the beta hydrogen. Now here, your alpha is a tertiary. It's a tertiary, so we're going to have a beta here, a beta here, and a beta here. Well, this beta, in this case, it doesn't matter because you're just going to pick one, and that's what you're going to get because they're all primaries. The betas are all primary. So they're equally substituted. Sometimes it'll matter. Okay, so the kinetics are second order. The mechanism is one step. So mechanism means, in the case for E2, you're going to have 3 curved arrows. And the more substituted halides are going to react the fastest. And this is going to be favored by strong bases. So, and you're going to have polar aprotic solvents. Okay, so this is a strong base, sodium tert butoxide, and it's sterically hindered. and you don't have to worry about it competing with an SN2 because it's a non-nucleophilic base. Okay, so now we got to look at our substrate and say, where is our leaving group? Okay, there's the leaving group. So let's make that our alpha, and let's classify its primary. So now we can locate a beta hydrogen, and we can draw that in. Sometimes you have to draw that in. And so the mechanism here is it's going to go there, and you're going to get your 3 curved arrows, and that's how you get your alkene. Okay, so remember I said that sometimes you'll see this written with a Z, and sometimes you'll read it with a S. Okay, it's a Russian, Zaitsev's rule. Okay, all it states is the more substituted double bond will be your major organic product. And the way you do that is you label your beta hydrogens, and then this is secondary, this is secondary, this is primary. So obviously one of the beta hydrogens is going to be the hydrogen that's on a secondary, and then you can draw in your product. This is minor product, disubstituted. If you notice whether you did this one or that one, you're going to get the same product. Okay, regioselectivity, this is just the region. That's what we're talking about. Which beta hydrogen is going to get which one? And that's the region. Which region is going to be selected. So that's just kind of like your vocabulary. So as always, you want to do the labeling. Find your alpha and say, oh, okay, that's a tertiary. And then we have 3 betas, and it's this beta that you would want to cleave. I just asked that you show your major product. Okay, so stereoselectivity in E2. You do have stereoselectivity in E2 because remember it's concerted. You remember in SN2 we had inversion of stereochemistry? So you have to do your dash and your wedge. Well, you don't have that on these because you don't have an sp3, but you will either get a cis or a trans. And I got to show you when you need to pay attention. Okay, a lot of times it won't matter. Here, just to take, so your beta hydrogen has to be anti. This is called anti-periplanar. What that means is this has to be 180 degrees. If you did a Newman projection on this, and then this was the bicarbon, then the hydrogen and your leaving group. So here you could go ahead and draw in, okay, you have your aromatic and your hydrogen here, and your front of your hydrogen here you have, and hopefully you can see that these phenyl groups are in the zigzag here, and then that's a hydrogen. So if you did your Newman projection, you would see that the hydrogen, the beta hydrogen that is taken is 180 degrees dihedral angle from the leaving group. This is what anti-periplanar means. And so if this happens, then your major product is going to be the trans dynamic. Because all right, so in this we have a secondary, and it says correct major elimination product. So that's how you know you have a strong base, and sometimes heat will be a trigger. Okay, because if you wanted SN2, you would do this at room temperatures. You wouldn't do heat. So here you have a strong base. So here you do your alpha, and you say, okay, I've got a secondary, so that means I've got 2 beta hydrogens. And so this is my beta hydrogen here, and this is a beta hydrogen here. And then I'm going to come in and take the beta hydrogen that's more substituted, and that's my leaving group. and you would get C as your answer. You know it can't be A or B because it says major elimination product, and then this is Zatsev's rule. And then that's compound C as your answer. All right, so that's a little bit about E2. You also have a great POGL exercise that talks about the stereochemistry requirement of your E2. So if you don't get all that information from these slides in this lecture, I do expect you to get that from your POGL exercise. E1 mechanism is just the unimolecular, so you're going to get elimination, you're going to get an alkene, and E1 is unimolecular, so it only the rate of your reaction only depends on the concentration of your substrate, your organic compound that has the leaving group. And this will always, remember if you get an always, but in science write it down, always be Zatsev's. So this is always going to be Zatsev's. You're going to be using a weak base, and it will always, well, mostly, yes, be polar protic solvent. Usually your base and your solvent are going to be the same thing, and they call that sovolysis. And so you'll just do this reaction in methanol, or you would do this reaction in water, or you would do this reaction in ethanol. And that's what you're going to see is typically methanol and ethanol and heat. All right, so the first thing you have to do though is you have to always, in an E1 or an SN1, generate a carbocation. And when you get a carbocation, always do the carbocation test. And remember, a tertiary, benzylic, allylic, these, this would be a benzylic carbocation. This would be an allylic carbocation. This would be a tertiary carbocation. These are always going to be more stable than a secondary. Okay, we don't even look at primaries if we can avoid it. Sometimes there's forcing conditions. So if you have a secondary and there can be either a hydride shift, that means a neighboring hydrogen. Even if it doesn't have a hydride shift, it will do a methyl shift. Okay, so hydride or methyl shifts will switcheroo a location with a carbocation in order to get these more stable carbocations. So here you have a carbocation. You have to show your stepwise mechanism. This is the mechanism. So the leaving group leaves to generate your carbocation. Now let's classify the carbocation. This is a tertiary. That means it has three neighbors. One, that if it switched place, the carbocation switched place, mean a hydride shift, that would be a primary. That is not better. That's a primary. That would be primary. So tertiary is the most stable. So now we can go on to the second step where we take, look at, you have a polar protic solvent and base. This is just done in water. And then that's going to deprotonate that to give you the always the Zatsev product. And so the energy reaction diagram is very similar to an SN1. In fact, that you have this valley for the carbocation intermediate. This would be the same thing. The leaving group leaves. Okay, so that would be the same. But here, this would be the little bit of difference because your transition state here, and it would show taking the beta hydrogen as opposed to being a nucleophile. Okay, the rate of an E1 reaction increases with the number of groups of carbons. So notice that the fastest ones are also tertiary. The SN1 and E1 stay the same on here. Your tertiary alkyl halides are also competing now with E2. So the way you see this and determine E1 over E2 is it needs to have a weak base, and it'll be water, it'll be methanol, it will be ethanol. These are weak, and they're also polar protic solvents. The strength of the base will determine whether you have E1 or E2. You see the negative charge? The strong bases favor the E2. Weaker bases like water and alcohol favor E1. That's how you know. So here we have methanol and heat. We have a secondary. We have a major product. Major. So what would it? So this would leave, and you would get your carbocation. And so there's your carbocation. This is the mechanism, E1 mechanism. And then you're going to have to say, okay, that's a secondary. So I've got to look at two neighbors. This would be a primary if it switched places with the carbocation. This would be a tertiary because we can do a methyl shift. This is called a methyl shift. And what happens is that CH3 actually takes its electrons and brings a whole methyl group. Why would a methyl group do that? That's how more stable it is. So now the methyl group's there and the carbocation changed places. So now we have a tertiary. So we switched out from a secondary to a tertiary. And now we have our nucleophile coming in, our weak nucleophile. Oh, I'm sorry. In this case, you would get, that's an alpha, and this is a beta for elimination. So that would be the elimination product. D for an E1. And before we leave this, I just want to say, see the heat? The heat would be why you would choose the E1 as your major as well. Okay, regioselectivity. Okay, regioselectivity of E1, I told you it's Zaitsev. Okay, it's your more substituted. So because you always get the alpha, it leaves. So when you get that, carbocation is always going to be more thermodynamically stable. In this case, this is your alpha and it is a tertiary. So if it switched places with this one, it'd be a primary. If it switched places with these two, it would be a secondary. So it's going to be more substituted. So then which beta hydrogen? It'll be the more substituted. So the water will come in and take that beta and give you your major product. It's first order. That's what the 1 means. That's a kinetic rate law. The rate equals whatever your substrate concentration is. There's going to be 2 steps. You're going to have the valley and the reaction diagram for your carbocation. And you're going to have to do your carbocation test. The more substituted, the faster. So tertiaries are going to be your fastest. Also, allylic and benzylic will be the fastest too. How do you decide between that and an E2? It's by the weaker bases, water and methanol, alcohols. You're going to have a great leading group and then polar protic solvents. So the problem with SM1 and E1, usually you're going to get a mixture. And that's usually what happens here. So a lot of times you might have to pay attention to it. If you get an SM1 E1, you're going to get a mixture. And so, but you get a carbocation and either the nucleophile will go after the carbon to get a substitution reaction, or your base can go after the beta hydrogen to get elimination. The stereochemistry of E2, this is where you need to look at your POGL for some really in-depth understanding. Antiparaplanar is the way this geometry, this is for E2. You have a strong base and you're going to have to sometimes rotate this. You might even have to look at a Newman projection to get the beta hydrogen where it's antiparaplanar. This is how it is antiparaplanar. Not such a big deal when you have rotation here around the single bond because it can rotate. Where you have problems is the this is where your POGL is good, when you have your leaving group on a ring. So what about something like this? Well, anytime you get a cyclohexane, you want to go back to the chair, folks, and draw the chair. And you want your leading group to be in the axial position. So you're going to put your leaving group in the axial position because it's going to flip, and it might be in this, 1% or 5% of the time. But this is where the reaction will occur. Here, if we have the methyl going down, see the methyl going down, then you have to draw in your hydrogen here. So the base here could not take the equatorial hydrogen. That will not happen. The base is going to take the axial, so this is called the diaxial, and so the base will take the diaxial, the hydrogen, the beta hydrogen, and the leaving group need to be diaxial to each other. So this is what this is, and then those electrons will go, and in that case, you won't get your Zatsev's product, which is the more substituted. You will get this compound here, which will be CH3, that alkene. So when you have rings and you don't have free rotation around that single bond, you have to draw the chair and you have to put the beta hydrogen in the diaxial leaving group. And you'll have to practice this. And so, like I said, we worry about this with the E2. This is the, instead of having an inversion of stereochemistry, we have to pay attention to anti-paraplanar. And so they're showing you this here. The base is going to take this hydrogen, this beta hydrogen, that is diaxial. You see, this is diaxial to the leaving group. There's your alpha. And the syn paraplanar does not happen because those electrons have to line up. These electrons have to go and do a backside attack towards that carbon to eject that leaving. Okay, so this is important. You need, even though this is the less stable, it does make it a little bit. You need to put this in the axial position in order to do elimination. And so this is an alpha carbon. It is a secondary, so we have two betas. So we have this beta and we have this beta hydrogen. And so when you put in these beta hydrogens, then your base can come and take one of these. In this case, it won't matter. And this is the mechanism to make that cyclohexene. Even though it's less stable, you need your leaving group in the axial position so it's diaxial. Okay, so which Newman projection represents an E2 reaction below? So, well, let's make sure that this is the right Newman projection. So this is that here, and so this is that carbon, the front carbon, and then your back carbon has the Br and the CH3, so that is correct. Let's look at this one. Here's the CH3. This isn't even the right Newman projection, right? Because if you did this, you would see that that's CH3 and Br, and then this back one is a CH3. So this is not the same compound. So 1A is the only one. And then what would your base do? Well, it's going to take the beta hydrogen. This is your alpha leaving group that's anti-periplanar. So it has to be here. This is going to kick in there and those leave. So it has to be anti-periplanar to the leaving group. So Newman projection A. This is that trans-diaxial geometry. The requirement is trans-diaxial geometry for the elimination. Sometimes that gives you the less stable isomer. Okay, so sometimes, and that's what you can get in E2. You can get a less stable. You can get we call that the Hoffman product. The less stable alkene, not the Zatsev's. E1, you always get the Zatsevs, and that's because you're getting the carbocation, and that's going to go to the more, there's going to rearrange, make a carbocation shift to always give you the more stable. And the more stable is going to end up giving you the most substituted alkene. So here they're showing you in this book that you need to put your leading group in the diaxial position. So this is axial, and then you look at your beta hydrogen. And so you can see the base takes the hydrogen. It will do a ring flip, through the flip, and to get you in the right conformation for the E2 elimination to occur. So whenever I get a chair and I'm doing eliminations or a cyclohexane, I always do the chair. So I cannot do these and figure out what the product is going to be without drawing the chair conformation. So I would recommend that you do this. So here we have the cis versus the trans. And when I draw these, I just go ahead and put the leading group in the axial position. So here I say, well, there. Okay, so we're going to put that up. And then what is cis? Okay, this has to go relative, it has to go up. So that's CH3. And then I have this one, I'll do the trans here. And here we're going to do Cl down. I'm going to put in the axial position. And then here we'll put the methyl up. The next one may methyl up. Okay, so now we're going to, this is our alpha. So where will we do our beta? This would be a beta. And this could be a beta. So in this one, this compound here, the base can choose either one of these, but the base is going to choose the beta hydrogen that's more substituted. And so this one would give you the more substituted alkene. This is tri-substituted. And this one, because this beta, this is your alpha, because this beta is blocked, this is the only beta it can choose from. So your base will take this beta hydrogen, and now this product would be, there's your double bond here, so that would be the least substituted. So this would be a Hoffman. So this is going to give you this product, whereas this one's going to give you this product. And that's what this is showing you. Here, you get the major product because the methyl is in the equatorial position. So you're going to choose the HB proton and get the more substitute. But in this trans isomer, when you draw this axial position is blocked. So then it is this beta hydrogen that's going to get removed. And it's showing you that here, that this is the only beta axial hydrogen that can be removed, the only one to react, and that's going to give you the disubstituted product. The Zatsevs is not the major product in this case. Okay, so when you get something like this, you're going to have to draw the conformation of the chair to solve the problem. This is how you solve the problem. So you draw your chair, and you're like, okay, I got to put the leading group in the axial position. And you know what, I can draw a better chair than that. So let's try this a little bit. Can we get a better chair? Okay. All right, we're gonna just, and you want to make sure you can see the up and down. So you want a little bit of a slant on your chair. Okay. And then so the bromine's coming down. D is like the isotope for hydrogen. So you're going to have to put the D in there. If that's going, this is down and that's down. It doesn't matter that it doesn't have to be down, but the relative has to be there. So I'm going to put that as a hydrogen. And then I'm going to put this is down. See how this one goes up, so that's up and that's down. So that's down and down. And then we have this isopropyl group is going to be up. So this is the hydrogen that's down, and that would be equatorial. This is hydrogen axial up. Now we find our leaving group, and we call that alpha carbon, and we say that's a secondary. So we have two betas. We have a beta and a beta. So we have two beta hydrogens. Which beta hydrogen will the base choose? It will choose the one that's diaxial, the transdiaxial. And so then if you want to, you can draw it like this before you make a two-dimensional. So you have this here, and you have this here, and you have now the D there. And so if you make that two-dimensional, if you need to, sometimes you need to, you can say, okay, there's there. You can choose the stereochemistry or not. And then we've got to get in our D, and our D's there. And then I would count 1, 2, 3, 1, 2, 3. Make sure it's right. It's just asking which compound is the intermediate conformation. So it's asking you for this. And so do you see that the Br has to be axial? So A is the answer. Okay, so comparisons for E1 or E2. E2, you're going to have these strong negatively charged bases. They're basically going to be hydroxides or alkoxides. And keep in mind, tertiary reacts fastest. And that's different than SN2. And then in your E1, you're always going to get Zatsevs, and you're going to have the weaker neutral bases. Now let's combine all of these. Now we have to decide, are we going to do an SN1, SN2, E1, or E2? So we have good nucleophiles that are weak bases. They're going to form substitution over elimination. So these are great nucleophiles, okay? So if you have these that are great nucleophiles, they're not bases. These are not bases. You know it's not bases. You know HBr is a strong acid. HI is a strong acid. These are not bases. So you might want to memorize that. So whenever you see these, you're going to think, oh, okay, and these have the negative charge. I'm going to go with SN2. So here, even though we have a primary, in here, this is going to be an SN2. Bulky bases are going to favor elimination. Okay, so bulky bases. These are your bulky bases. This one here is potassium tert butoxide. You can see it like that. And they are not going to be, these are not nucleophiles, non-nucleophiles. They're not going to be nucleophiles, so they are going to do the base. And if it's strong, whenever you have a negative charge, go E2. And I would choose most of these to be E2. This is an alpha, it's a primary, so there's only one hydrogen to choose from. That's going to be an E2. Tertiary alkyl halides, they can do either E2 or SN1. Okay, so that's what we're looking at. E2 or SN1. Here's a tertiary. If you have a strong base, it's going to be an E2 always. Here's a tertiary. You got a weak nucleophile. I'm going to go with an SN1 product. So you could also, you usually get mixtures too. So if I said heat, this would be your major product. Otherwise, you can do 50-50. On something like this, I would say, what's the major elimination product, or maybe what's the major substitution? Okay, so with strong nucleophiles, you're going to get substitution occurs. So a primary is going to be a strong nucleophile. So that's an SN2. Bulky bases are going to do E2. Now secondary, we got to decide between SN2. These are the ones you're like, could be any of them, right? So if it's a strong base, you're going to probably get a mixture. If it's heat, then I would go with my major product being E2. If you have a bulky base, it's going to be E2 because it's not nucleophile. This is a non-nucleophile philic base and it's strong, so it's going to be E2. Here we have a secondary, we have weak. I'm going to go with an SN1, but you're also going to get a mixture whenever you do SN1. If you have heat, then you might get a little bit more. You might get 60% E1 and 40% SN1. And so this is kind of a chart that just shows, first of all, always classify your substrate and then look at your nucleophile and decide whether it's a strong base or is it a nucleophile or is it just a big bulky base, and kind of try to classify that. And that I would recommend definitely doing your POGLs on these and work problems because that's where the learning occurs.